All right, welcome everybody to video 14. What we're going to be looking at in this video in this lesson is double angle and half angle identities. These will be your final two sets of identities that we're going to focus on. And this is really going to be the first set of identities that you'll really see a direct application to if you move on and take a calculus class. And so the way that these are formatted, how we use them is going to be very important, and just recognizing how these can be used will be very, very important, especially by the end of Cal 1, definitely, which is AB, and then definitely in BC. Again, really depending on if you're pursuing what kind of major or what kind of field of study you're going to pursue. These are the ones that I would definitely try to memorize, other than Pythagorean and the reciprocals in those. All right, and so the goal here again is to use angle, sum, and difference identities. So the identities that were talked about in the previous video, to actually create these new sets of identities. So all of this is going to stem from what we know already, and being able to work in and with these identities. So the first ones we're going to start out with is the double angle identities, and we're going to work first with sine. Now, what the double angle identities are, just to give you a basic essentially setup for my ultimate goal here, is we're really just going to try and define it for sine and cosine. So I'm looking for sine of 2a. So again, if I was to double the angle and then take the sine of it, and then cosine of 2a. Again, if I was to double the angle, so do 2 times my angle, and then take the cosine of that. Now, in the actual lesson notes that accompany this video, you'll actually see that I go through and show you how to do tangent of 2a. It's not as important to kind of see where this comes from. You can kind of see my work, or I can leave that as an exercise for you to try out and see if you can get to it. It's something you could do a discussion post on, and see if you can format where this comes from. I'm only going to focus in this video on sine and cosine specifically, and how these are created. Now, from our goals, it's kind of given away that we're going to use the angle, sum, or difference identities to do it. So for example, I just want to put out the sine angle sum formula again. So sine of A plus B is equal to sine of A cosine of B plus cosine of A sine of B. Again, you can see this on the formula sheet posted on PowerSchool Learning. Now, when I'm doing the double angle identity, understand that when I have sine of 2a, another way to look at that would be to say sine of a plus a. In other words, remember, multiplication is just repeated addition. So saying 2 times a really is just saying I'm adding a with itself, right? A plus a. And if I look at it that way, notice I'm essentially saying I have a plus, well, instead of having b, I'm just having another a. So I can actually use my angle sum formula, and just in place of b, I'm just going to use another a. So the formula would essentially be sine of a cosine of a plus cosine of a sine of a. Right? There's just no more b's. Everything's in terms of a. And to finish this one out, this piece, this expression here, because it's multiplication between the two, can be looked at in any order. So you can read the second piece here as cosine A sine A, or sine A cosine A, which means it matches the first one. I'm adding two expressions that are literally the same. And just like we talked about with how I can write 2a as a plus a, I can express this as 2 sine of a cosine of a, because I have two of them. And so what this essentially then creates is the first double angle identity specifically for sine of 2a. Now, this formula here we'll go through in an example and how we can kind of use it and rewrite it. This is one that you will see a ton in future math classes, depending on how far you go. This is one I would, again, highly encourage you to actually memorize because of its use later on. And so that way, when you see it, you'll be ready to expand it or condense and be able to work with it. All right, so moving on, because we need to design, or not design, but come up with cosine of 2a. We do this very, very similar to how we did sine of 2a. We are going to now use and I was tempted to write it, but I don't think I will. We're going to use the the angle sum for cosine. All right, cosine of 2a is the same thing as saying cosine of a plus a. In other words, not b. a plus a, meaning that this is an angle sum type problem. We can use the cosine piece of that formula. So I'd encourage you to again look back at that formula sheet to see that identity. Well, writing this out, this would be cosine of a times cosine of a minus sine of a and then sine of a. And I can simplify this then to say cosine squared, because there are two of them being multiplied, minus sine squared. And so this tells me then the formula for the double angle of cosine. Cosine of 2 times my angle is equal to cosine squared of my angle minus sine squared of my angle. Very, very similar here to Pythagorean, but notice the order and that it's also subtraction. So just be very, very careful and don't intermix the two. All right, now, one of the trickiest things about cosine of 2a, though, is that this isn't the only expression, the only identity for cosine of 2a. Because it contains cosine squared and sine squared, I can use the Pythagorean identity to actually rewrite this another two different ways. So for cosine of 2a, there's actually three different pieces to it total when we're doing double angle. Now, to help show you where that comes from, again, just as a reminder, from Pythagorean, that sine squared of a is equal to 1 minus cosine squared of a. In other words, I can replace sine squared with this expression. And so if I was to do that, I would have cosine of 2a is equal to cosine squared of a minus that expression 1 minus cosine squared. Now distributing the negative, this would give me 2 cosine squared minus 1. And so I essentially now have a second formula, second identity for cosine of 2a that involves just cosine. And I can do the same thing by, instead of replacing sine, what if I wanted to replace cosine? Well, cosine squared from Pythagorean is 1 minus sine squared. And so I can replace cosine squared in the original here with that. And so then I would have cosine of 2a is equal to 1 minus sine squared minus sine squared in the original. And this would be equal to 1 minus 2 sine squared of a. And this is equal to cosine of 2a. And so I have the first one, the second one, and the third one. And these are the only ones, again, that we're going to focus on in this lesson. Again, on the lesson plan that you can see on PowerSchool Learning, you'll see me walk through tangent. For now, I'm going to stop here. But I am going to put this all together. And again, you'll see this on the formula sheet written nice and neat. And this is essentially what you're going to see. For the double angle identities, sine of 2a is equal to 2 sine a cosine a, which you see here. And then cosine 2a has three different forms. The first one that we came up with, the second, and the third that we came up with. Each of these other two here stemming from this one and using Pythagorean to help rewrite it. So these are the essential four different double angle identities that you are responsible for. Again, I wrote tangent up there. I'm not going to make you responsible for that. I just wanted to show you what that one would look like if you were wondering. But these are the ones that you'll need to use, especially in this first example. So let's take a look at the example. Try to have the formula sheet next to you because, again, I can't keep it on the screen at the same time. All right, so example 1, rewrite each of the following trig expressions below in one step. In other words, my goal is just to do this once. All right, and so take an A. So I have 2 sine of 3x times cosine of 3x. Well, notice that this form right here, 2 sine of my angle, cosine of my angle, this is the double angle for sine. And essentially, this would simplify down into sine 2 times my angle, which is 3x here in this problem. So this can be simplified to sine of 6x. Now notice in this problem here that my a, in terms of the identity and in terms of the formula, was equal to 3x. And so that would be my first initial step and what I would encourage as we go through and look at these. What is my A and what is my B as I go through and simplify? And then we can follow the identity left or right in terms of if I'm condensing or expanding and then continuing to use that as necessary. All right, so B, this is tricky, so be careful with this one. Cosine squared of 40 degrees plus sine squared of 40 degrees. Now, because we just have been looking at and discussing double angles, you're going to be tempted to immediately use the double angle formula for this. The thing that you have to understand is that this is a plus and the double angle is a minus. So because it's plus, what would this be equal to? Hopefully you're saying 1, because this is Pythagorean, right? Sine squared plus cosine squared will always be 1 when the angles match like this. It doesn't matter what that angle is. So it can be 40, 60, 35, 102, whatever. As long as it's cosine squared of that angle plus sine squared of the same angle, this answer will always be 1. All right, now C, this is where they'll kind of go back. So what if instead, though, it was a minus? So cosine squared minus sine squared. All right, well, this is looking at the double angle for cosine, that very first one, where specifically my A is 40 degrees. So this would simplify down to cosine of 80. Oops, sorry. And again, the A in that formula and in this example would be 40 degrees. So my answer here would be just cosine of 80. All right, for D, I have 1 minus 2 times sine squared of y minus 5. So this format you'll see under the cosine of 2a. So I just need to know what my angle is. Well, my angle is everything that's in the parentheses of sine squared, which in this case is y minus 5. So then just simplifying that, this will be 2y, almost wrote that, 10. And again, this is where a is equal to y minus 5, specifically. All right, looking at E. So I have sine of 30, cosine of 40, plus cosine of 30, and sine of 40. All right, now notice this is not double angle. This would be angle sum. Now, because it's sine and cosine, this is telling me that I'm using sine, and because it's plus, that's how I know it's plus on the inside. So two angles, my A and B, are 30 and 40. So I can condense this down to saying sine of 70. For F, I have 2 cosine squared, 2w, minus 1. This is the double angle for cosine, specifically where my angle is 2w. So I can simplify this down to 4w. This again is where A is 2w, and then using the formula. All right, so that's example 1. So this whole goal here is just condensing, recognizing the formulas, and working with them. All right, now that's double angle for now. Let's move on into half angle. All right, so if double angle was taking sine, or having an angle, doubling it, and then taking sine or cosine, half angle is doing the opposite of it. So for example, I'm taking an angle and dividing it by 2, and then I want to take the sine of that. Or what if I was doing cosine of a divided by 2, etc. Again, we're not going to worry about tangent here. We're just going to focus on sine and cosine. All right, now both of these definitions will actually stem from the two double angles for cosine. Specifically, cosine of 2a is equal to 2 cosine squared of a minus 1. And then we had cosine of 2a is equal to 1 minus 2 sine squared of a. Now what I'm going to do here is, so because I don't want the a's to be duplicated, I'm actually going to look at this problem and call this formula and use an x instead for both of these. Remember, a just kind of represents whatever you want to plug in. So I'm going to use an x here. And let's start with this one here. And I'm actually going to go through and I'm going to solve for cosine squared of x. I want to get this piece by itself in this first formula here. So that means my first step is to add the 1. So I'll have 1 plus cosine of 2x is equal to 2 cosine squared of x. And then divide by 2. I get cosine squared is equal to 1 plus cosine of 2x all over 2. Now immediately this is actually going to be a important formula right here. This is one that you will use in calculus a lot. Essentially this is called the power reducing formula. It says that if you essentially have cosine squared and I need to simplify it down, I can rewrite it as 1 plus cosine of 2x. Notice how that cosine is no longer squared. And then all of this is divided by 2. This identity here is very, very important in calculus BC. You kind of see this in AB a little bit, mostly used in Cal 2 in terms of calculus. Now, this right now is my end goal. Now, what I'm going to do to get to the final step here is remember that I'm trying to find half angle, right? So I'm trying to do a divided by 2. And so what I'm going to do is I'm actually going to let x be equal to a divided by 2. Which means, notice that if I was to substitute this in, I would get cosine squared of a over 2 is equal to 1 plus cosine. Well, if I do 2 times x, the 2's are going to cancel and leaves me with just cosine of a. And this will be over 2. And then by taking the square root, I get cosine of a over 2 is equal to plus or minus root 1 plus cosine of a over 2. This is the half angle identity. All right, it's pretty nasty looking. Now, this one you're going to use in calculus, so I would just say be familiar with this, but this is the actual half angle identity. Notice it's really just kind of a rewritten and then taking the square root of it. So that way it's kind of getting rid of the 2x on the right-hand side here and getting it so it's just cosine of a. And notice by doing that, we have to change the left-hand side. And that's why this one has such a unique name versus the power reducing that you see here. All right, and so this is the first formula that we have. One thing you'll notice, and we'll talk about this in one of the examples in a minute, is the plus and minus. Remember that when you are introducing a square root to the problem, so when I have to take the square root here, there are always two different answers we have to account for. Therefore, even here, we have to have pluses and minuses. We can't just abandon that operation. So we have to keep that. All right, now this is just one of the formulas that we care for. That covers this cosine of a over 2. So I need to find sine of a over 2. Well, that just means we're going to use this one. All right, and notice how this has a sine in it. So just like here for cosine, we solved for cosine squared. I'm now going to take that second one, and I'm going to solve for sine squared. I would encourage you, if you want to at this point, pause the video and see if you can solve for sine squared on your own, just as an exercise. But I'll continue here to go through and do that. So just to write it, since I don't have it on the screen anymore, remember that the formula was cosine of 2x is equal to 1 minus 2 sine squared of x. And so again, I want to solve for this sine squared here. So that means I'm going to subtract 1. So I'll get cosine of 2x minus 1 is equal to negative 2 sine squared of x. Now I'm going to divide by negative 2. So because I'm dividing by negative 2, that division by negative is going to change the signs over here on this left-hand side. Right? So instead of being cosine minus 1, it's now going to be 1 minus cosine. So I'm going to go ahead and write that like so, divided by 2. And this is going to be equal to sine squared. All right, now, just like last time, this right here is a really important formula. This is the power reducing for sine. So anytime you have sine squared, if I want to rewrite it, notice that it's actually rewritten in terms of cosine, specifically 1 minus cosine of 2x, all divided by 2. This, again, is very, very useful in calculus. All right, we're not going to worry about it too much right now, but again, later on, you will see this. So it's something to keep in your back pocket if you're going to go further in terms of math classes. Now, that's not my end goal here. Just like last time, I'm going to let x be equal to a divided by 2. And so plugging that in, I would get sine squared of a over 2 is equal to 1 minus cosine of just a divided by 2. And then taking the square root, I get sine of a over 2 is equal to plus or minus the square root of 1 minus cosine of a over 2. Here's the half angle identity for sine. Notice that the only difference between this one and this one, the cosine half angle and the sine half angle, is that for sine it's a minus on the inside and for cosine it's a plus. That's really the only big change there. Notice it's the exact same pieces, same square roots, same fraction, and all of that. So in terms of memory, I don't think it's super hard to memorize these. Again, they will be provided, so you don't have to worry about that. But just something to be aware of in terms of the way that they're created, because they all stem again from the same identity, right? Cosine of 2a, just two different forms of it. This is the half angles, and so I've got the half angle identities rewritten here, so you can kind of see them side by side. And again, kind of noticing again that really the only difference is this is minus for sine versus plus here for cosine. So the next example is actually going to walk through how we use it, and it's also going to establish when we need to choose between the plus and the minus, right? Is the answer going to always be plus or minus, or will it be one or the other? All right, so I'm going to talk about that here in example 2. All right, so sketch the given angle and then use the half angle identities to calculate the exact value. Now again, exact value, recall, is always pointing out, go look at the unit circle, right? Always. All right, so cosine of 7 pi over 8. Now in this problem, 7 pi over 8, if I was to sketch it, notice it's just less than a whole pi, right? 7 over 8, which means I am just shy of making one semicircle. So 7 pi over 8 sits in the second quadrant, which means cosine in the second quadrant is negative. That means the answer to this has to be negative. Keep that in mind. All right, now the next thing that I'm going to do is, because I know that I want to use half angle for this, I'm going through and I'm looking at this in terms of x is my 7 pi over 8. Right, that's what my x is. That's what the input here is. Now, from our formatting of how we went through and created the formulas, remember that I set x equal to a over 2. We'll solve for a here in this equation. Well, I need to multiply by 2 on both sides. This would give me 14 pi over 8. Dividing both of these by 2, I get 7 pi over 4. In other words, that's my a. That's the a that I'm going to be using in the formula for cosine. And that's how I get it. Right, so this a over 2 here on the inside of the parentheses, what that represents is whatever angle I'm taking the cosine or sine of. So that means that a divided by 2 has to be equal to 7 pi over 8. And that's why I can get and set this up here and why we did it earlier. All right, and so I'm going to do this again in a minute so you can kind of see it. But this tells me what my a is. So when I use my formula, I can now just kind of plug and chug. In other words, when I'm trying to find cosine of 7 pi over 8, that is the same thing as finding the cosine of 7 pi over 4 divided by 2, right? Because that's what my a is. Well, using the identity, I know this is equal to plus or minus square root of 1 plus cosine of a, so cosine of 7 pi over 4, and then dividing all of that by 2. Now, I know that my answer again has to be negative, which means I can erase the plus sign, because this answer here should have a minus in it. Now I just need to go through and essentially simplify and evaluate, right? So I get negative on the outside, square root, 1 plus, well, cosine of 7 pi over 4. I can go to the unit circle for that. That's going to be root 2 over 2. All right, I'm going to simplify this a little bit more by going through and dividing both of these by 2. So this is 1/2 plus root 2 over 4. Making this one fraction, I get the square root of 2 plus root 2 all over 4. And taking the square root of the denominator, this would give me the square root of the top, which is just 2. Hold on, let me rewrite that. This would be square root of 2 plus root 2 all over 2. Negative. I dropped the negative. There's my final for A. Cosine of 7 pi over 8 is negative square root 2 plus root 2 all divided by 2. It is a nasty looking answer. So just know that I completely understand and I empathize with you in that. I wish it was a little bit neater, but that does equal the exact value. On an assessment for half angle, I need to see at least through this step. I would like to see at least to here as a final answer, making it one fraction on the inside. Simplifying it again would be very, very nice. But again, I think in terms of asking for everybody, I think everybody, I would highly encourage you to get to this step right here. All right, so let's look at 7 pi over 12 now if I'm doing the sine of it. And I want to do half angle. Okay, so here, I just want to sketch this again, just to get a sense of whether this answer should be positive or negative. Now, when I do 7 pi over 12, notice half of 12 would be 6. So 7 is a little bit more than that. Not by much, though. And it's not a whole pi, so I'm sitting somewhere again in the second quadrant. Now, sign in the second quadrant is positive, so my answer should be positive. All right, now when we go through and do this, though, I'm essentially saying x is 7 pi over 12. If I set this equal to a over 2, multiplying 2 on the other side, we'll get that a is equal to 7 pi over 6. Notice again how that's an angle on the unit circle, so that means I can do the exact value stuff. All right, so I know that sine of 7 pi over 12 is equal to sine of 7 pi over 6 divided by 2, which is equal to a positive square root of 1 minus cosine of a, which is 7 pi over 6, all divided by 2. All right, finding cosine of 7 pi over 6, I get square root 1 minus cosine of 7 pi over 6 is negative root 3 over 2. This is all divided by 2. So then this will give me the square root of 1 over 2 plus root 3 over 4, which if you notice like last time, simplifies down to 2 plus root 3 all over 2. Because this inside piece right here, once I find my common denominator, it would be 2 plus radical 3 all over 4. I can square root the bottom, but I can't square root the top, so that's why the square root will stay, but I will write it as all over 2. All right, and so that's the answer for part B, and essentially using the half angle. The simplification is nasty. You will see square roots within square roots. Please don't let that alarm you. Kind of just take away from this the ability to work through some problems that just don't look great. And that just is what happens in more advanced math classes. Okay, and so we're almost through in terms of looking at formulas and stuff. That's it for half angles, and again, that's it for all of the identity stuff that we're going to be looking at in terms of precalculus. And so the final question that I want to kind of give you and kind of walk through with you is really just going to put all of the identities and stuff together in terms of some problems to try and simplify and find the exact value. So just giving you a chance to see how everything kind of plays a role. And so example 3, let's practice applying specifically half angle identities to these next 4 again. So just so you can see again how these work. And then we're going to try to rewrite and evaluate specifically using the half angles. Okay, and so in A, this is probably the one that's the most disgusting. And when you look at it, you'll notice that it also is in terms of tangent. All right, it's not necessarily in terms of sine or cosine, and I didn't give you tangent in terms of half angle. And here's kind of the reason why I didn't. If we think about my quotient identity for tangent, tangent is sine over cosine. In other words, if I was to find sine of 11 pi over 12 and divide it by cosine of 11 pi over 12, this would give me the same answer as doing tangent of 11 pi over 12. Well, individually, these two things here, we do know the half angle identities for. And so that's actually what I'm going to do. I'm going to go through and use half angle for sine and use half angle for cosine, and then construct them in terms of tangent, which is taking my answer from sine and dividing it by what we get from cosine. All right, and so I'm going to go through and I'm going to find sine of 11 pi over 12, get an answer for that, and then I'm going to divide it by cosine. All right, well, just like last time, I'm going to let x be 11 pi over 12, which is equal to a over 2. My a in this case is 11 pi over 6. So this will be sine of 11 pi over 6 divided by 2. Now 11 pi over 12 is in the second quadrant, so I know that has to be positive. And we did 7 pi, but we didn't do, yeah, okay. I just wanted to double check. All right, and so we've got 11 pi over 6 over 2. Okay, and then I know that this is going to be positive as an answer, square root 1 minus cosine of 11 pi over 6 divided by 2. This will be square root 1 minus 1 root 3 over 2 all over 2, which comes out to be square root, that's terrible, square root of 2 minus radical 3 all over 2, once you simplify it. All right, now I want to find cosine. It's not letting me erase that. Okay, there we go. I just want to get it out of the way. Let's do cosine now of 11 pi over 12, and then we'll construct our answer for tangent. All right, so this would be cosine of 11 pi over 6 divided by 2. All right, which means this answer, because I'm looking at 11 pi over 12, this is in quadrant 2, this answer is going to be negative, and it will be square root of 1 plus cosine of 11 pi over 6 all over 2, which is equal to negative square root 1 plus radical 3 all over 2, or negative root 2 plus root 3 all over 2. So this is my answer for cosine. This was my answer for sine. And so to do tangent, I'm going to take my sine answer and divide it by this. Now, when I divide it by this, remember that's essentially multiplying by the reciprocal. So just to rewrite it, so you can see this out. This is pretty complex. This would be tangent of 11 pi over 12 is equal to my answer for sine, which was root 2 minus radical 3 over 2 times negative 2 over radical 2 plus radical 3. Again, because I'm dividing by my cosine answer, and my cosine answer is a fraction, I'm keep changing and flipping that. And when I do that, notice these 2's here are going to cancel. And so I would be left with a negative overall square root of 2 minus radical 3 over 2 radical 2 plus radical 3. And nothing can be canceled out. Really, the only thing you could do, and I would argue this looks a little bit better, is just to make it one big square root and say 2 minus radical 3 over 2 plus radical 3. But, you know, it's just kind of up to you or the teacher. So either one of these answers works. And there's my answer for tangent. So you can kind of see why tangent's so gross. Also why we didn't really construct the half angle for tangent. So let's move on to B. And B, these next ones are going to be a little bit easier, which is nice after that one. So 1 minus square root of 1 minus cosine of 6x. So square root 1 minus cosine of 6x all over 2. And so I want to use one of my identities for this. Now, the minus is what kind of gives this away here. That for the half angle, this is referring to sine, right? And when we're doing sine, remember that it's whatever a is, so whatever's on the inside of the parentheses, divided by 2. So in this case, that would be 6x over 2. And then simplifying this, I would get sine of 3x. And this is my final answer. This is why the directions say to rewrite or evaluate, because we don't really know what x is. X is a variable. Then I can actually just leave this. That's my final expression here. Again, I know this is sine because it's minus cosine. Also in the formula, I know that whatever cosine of a is, in terms of the half angle, it's a divided by 2. So a is 6x. So then therefore I do 6x divided by 2. And then that gives me sine of 3x. All right, let's take a look at C. And then we have one more left, and that's it. All right, so C is 2 sine squared of x over 2. So 2 sine squared of x over 2. And then I think it's plus cosine of x. All right, the whole goal here again is to essentially simplify using the half angles to rewrite it because we don't have an x. All right, so I need to work with this part right here. So sine squared of x over 2. Now, I can look at this as 2 sine of x over 2 squared. All right, that's really what that square is doing. It's saying find sine of x over 2 and then square that result. Well, sine of x over 2 is literally telling me to use the half angle formula. So this would be 2 on the outside bracket. Well, the formula tells me plus or minus square root 1 minus cosine of x all over 2. I'm squaring this result. and the extra cosine on the outside just drops down. Now, the square is going to cancel out the square root, leaving me with 2 times 1 minus cosine of x over 2. Well, 2 up top, 2 on the bottom means the 2's will cancel. So then I'm left with 1 minus cosine x plus cosine x, which means the answer is just 1. So everything simplifies down. All right, this leaves us now with the final problem, D, which says to find cosine of x over 2 if tangent of x is equal to negative 4 over 3, if I remember right, and sine x is positive. All right, now we saw this when we were doing solving problems and working through trig stuff. Before I even get to cosine of x over 2, I want to focus on this part right here and what it's telling me. Right, I know that tangent is a negative 4 over 3. Well, just in terms of if I want to sketch out where x would sit, I know that tangent is negative in quadrant 2 and in quadrant 4. Well, only one of these quadrants is signed positive, right? And that is here in quadrant 2. So that means if I was to actually sketch, if I knew what x was, x sits somewhere over here in quadrant 2. Where even more so, if I was to actually sketch my reference triangle for it, I know that the opposite side is 4 and the adjacent side has to be a negative 3 because tangent is opposite over adjacent, right? It would be 4 over 3. The negative goes with the 3 because we're in quadrant 2. I have to take a step to the left and then I go up. Well, this also establishes what the hypotenuse is, which is 5. Right, it's a 3, 4, 5 triangle. Now this is going to be very, very important because if I go through and I use the formula for cosine of x over 2, right, if I just did the half angle formula, this would be equal to plus or minus the square root of 1 plus cosine of x all over 2. And if I didn't know what I've got boxed off here, then this would just be the answer, right? It would just be asking you, just rewrite the formula. But because I know about these facts about x, I can actually go through and say what cosine of x is, right? Cosine of x is negative 3 over 5. So I can say 1 plus negative 3/5 all over 2, which means I can simplify this down a little bit more. 1 plus negative 3/5, or 1 minus 3 over 5 is 2/5 divided by 2. The 2's would cancel, so I'd get plus or minus radical 1 over 5. Well, breaking this up, this will give me plus or minus, well, the square root of 1 is 1. Well, root 5 I can't take. And then to rationalize this, I get root 5 over 5. So in other words, this is what cosine of x over 2 is. Now here's my question to you. Is the answer positive or is the answer negative? And that's the tricky part. All right, well, if x is in quadrant 1, excuse me, if x is in quadrant, sorry, if x over 2, hold on, I'm screwing up. All right, if x is in quadrant 2, right, x traveled to here based on what we knew. If you were to take an angle in quadrant 2 and divide it by 2, what quadrant do you have to be in? So I would argue that x has to be in quadrant 1, meaning that because I'm in quadrant 1, cosine of x over 2 has to be positive. The interesting thing is what happens if x is something that is coterminal. So let's say x is in quadrant 2, but it's greater than 360 or greater than 2 pi. Then where would x over 2 be? And could the answer then therefore be negative? And so I think it's a really interesting thought to it. So for now, I'm actually just going to leave the plus and minus on it because we don't really know that x is specifically between 0 and 2 pi. I just know what tangent of that is and what sine of that is. And so I'll kind of leave that as an exercise. You can even talk about it as a discussion post if you would like to. Again, this idea is should the answer be plus or should the answer be negative in this particular problem. Okay, so hopefully from what you've seen is that the half angle identity for just in general are pretty complex. And so I just want to kind of rewrite them right here again. We talked about in this video double angle identities. and we talked about half angle identities. Both of these very, very important if you were to continue education into higher math classes and harder math classes. So those formulas again, sine of 2a. So if you were to double your angle, this would be the same thing as doing 2 times sine of your angle and cosine of your angle. If you have cosine of double your angle, there are 3 different ways that you can find that answer. It's cosine squared minus sine squared, 2 cosine squared minus 1, or 1 minus 2 sine squared. Again, the video gets into tangent. I'll leave that, or the lesson gets into tangent if you'd like to see that on paper, or again, tangent as an exercise. Half angle formulas, we saw that again just recently. If you are dividing your angle in half, then this answer comes out to be plus or minus the square root of 1 minus cosine of your angle divided by 2. And if you were to do cosine of your angle cut in half, that is plus or minus the square root of 1 plus cosine of angle A over 2. Again, there's the power reducing formulas that we saw earlier that are very useful in calculus, but these are the only ones, again, that you need to know. In terms of what you need to kind of, again, walk away from this, what you'll see in the practice, being able to rewrite back and forth. Again, I think half angles are the hardest ones, so make sure you look at those practice problems. And if you need any extra practice, please let me know and I can post some or give you some during the virtual classes. We can take a look at it. For now, that's it. We are done with the identities and we are pretty much done with the trigonometry portion for mod 5 and for this class. We'll see some more trig and as we continue into vectors, but it will not be as trig heavy as we've seen so far. So again, let me know if you have any questions. Make sure you do your discussion posts and hopefully I'll see you at some of the virtual classes. Thanks for watching.